Hello everyone. Today we are going to see about measures of ductility. Its definition, importance of ductility, and it is based on tensile testing of materials. First, let us see what is meant by ductility. Ductility is the ability of a material to stretch or deform plastically before it breaks. Before it breaks. In simple words, it tells us how much a material can be pulled before fracture occurs. For example, a rubber band stretches a lot before breaking, so it behaves like a highly ductile material. But something like chalk breaks suddenly without stretching, so it behaves like a brittle material. So ductility basically tells us whether a material will fail suddenly or gradually. Why do we measure ductility? Measuring ductility is very important in engineering and material science for three main reasons. First, it tells us how much a metal can be shaped during manufacturing processes such as rolling, forging, extrusion, and drawing. If a material has a low ductility, it may crack during shaping. Second, ductility helps designers understand how safe a material is under load. A ductile material usually gives a warning before a failure by deforming. But a brittle material may break suddenly without warning, which is dangerous in structures. Third, ductility can also indicate material quality. Change in composition, impurities, or heat treatment often affect ductility. So, engineers sometimes use ductility as a quality check. Tensile test overview. In this, to measure a ductility, we perform a tensile test. In a tensile test, a specimen of standard shape is pulled from both ends until it breaks. During this process, we record how much it stretches and how its cross section changes. From this test, we can calculate different mechanical properties, but today we focus only on the measures of a ductility. Two main measures of ductility are elong- elongation and reduction of area. Both are expressed as a percentage values. Measure elongation. Elongation measures how much the length of the specimen increases before the fraction. The formula is EF is equal to L F minus L naught divided by L naught, where LF is a final length and L naught is an original length. It is also expressed in percentage. Reduction of area. Reduction of area measures how much the cross section of a specimen decreases at the fracture point. The formula is Q is equal to A naught minus A divided by A naught, which is where A naught is an original area and A is a final area. It is also expressed in percentage. Necking, when a specimen is stretched during a tensile test, for deformation does not occur uniformly throughout its length. Instead, most of the deformation happens in one small region called the neck. This is the place where the specimen becomes thinner before breaking. Because of this, elongation depends on something called the gauge length, which is the length over which we measure extensions. There is an one important point, which is when there is a smaller gauge length, elongation value will be larger, and vice versa. So, whenever elongation is reported, the gauge length must always be mentioned. Otherwise, the value can be misleading. In this, the reduction of area is more reliable because reduction of area does not depend on the gauge length because it is measured only at the fracture region. That means it always represents a local deformation as the failure point. So that many engineers considered reduction of area is more reliable for a measure of ductility than elongation. There is also another point. There is a relationship between the reduction of area and elongation near fraction. During plastic deformation, the volume of the specimen remains almost constant from so that we can know that AL is equal to A naught into L naught. From that we know that from area of reduction we know that A naught minus A divided by A naught, which give after we rearranging, we can see that L by L naught is equal to A by A naught by A is equal to 1 divided by 1 minus Q. For a elongation near fracture, we can obtain that uh, E sorry Q divided by 1 minus Q. From this formula helps us calculate elongation near the fracture region using a reduction of area. This is very useful because it removes error caused by the gas length difference. Next is another important measure is a uniform elongation. Uniform elongation means elongation measured only up to the point where necking begins, um, not until when the fracture is happened. Why is this useful? Because before necking starts, deformation is uniform along the entire specimen. After the necking starts, deformation becomes localized. Uniform elongation is very important in manufacturing processes like sheet metal forming, where uniform stretching is required. Practical engineering importance. Understanding ductility is very important in real engineering applications. For examples, bridges, buildings needs a ductile material so they deform before failure. Car bodies need ductility to absorb energy during impact. Next, metal forming industries require high ductility materials for shaping operations. Also, materials with a very low ductility can fail suddenly, so it can also lead to the catastrophic accidents. Simple comparison between ductile and brittle materials. In ductile, they stretch a lot and they show necking and absorb more energy before fracture fails gradually, and it has a rough surface and it shows us a cup and cone shape, while in brittle it it stretches a very little and breaks suddenly, and it absorbs a very less energy and fail without warning, and it has a clean break and a flat surface. So brittle breaks suddenly and ductile breaks um, with warning. So it is better to have a ductile material. To conclude this, ductility is the ability of a material to stretch before breaking. It is an it is an important mechanical property used in design, manufacturing, and quality control. The two The two main measures of ductility are elongation and reduction of area. Reduction of area is often more reliable because it is independent of gauge length. We can also calculate elongation near a fracture using reduction of area, and uniform elongation tells us how much a material stretches before necking begins. Understanding the ductility helps engineers choose safe and suitable materials for real world applications. Thank you.